This is a lesson on mutual and self-inductance in the unit on inductance in circuits. We're at the level of university physics. Just to review, in order to supplement your foundation in your understanding of electromagnetic induction, in order to have a better handle on the concepts of inductors and application, especially in regard to electromagnetic energy storage as we head towards LC and RLC circuits. So this is a foundation in inductance, and inductance begins with electromagnetic induction, which is Faraday's law and Lenz's law. And you can look at a prior lesson in induction, the changing magnetic flux. So those are the foundational concepts if you're not strong on electromagnetic induction and changing magnetic flux, what magnetic flux is. You will want to review those videos. We're going to remember that there's three ways in which flux can change, right? We have a delta flux over delta T in Faraday's law. And flux is related to the area of a loop, the magnetic field through a loop, and the angle between those two vectors, the area vector and the magnetic field vector. So there's different ways that it can change, and what we're going to focus on is number 2 here. The magnetic field through the loop changes somehow. So in order to isolate a little bit more than that, when we take a differential, and when I introduce this, I just use a delta. But of course, if we're calculus based, we can draw a d flux over dt in here, a dB over dt in here, and take a straight differential. And we can see that the number of loops can stay the same, the area can stay the same, the angle between the area vector and the magnetic field can stay the same. And we're focusing on how that magnetic field in going through that loop changes. So there's a couple of different examples that I showed here. We can just pull a magnet in and out of a loop. That would be a changing magnetic field. Here's the tabletop example from Cutnell and Johnson. If I just move a loop through a non-constant magnetic field, I'll get an electromagnetic induction there. And also if I just have a changing magnetic field somehow, I don't know how it changes, but the magnetic field changes, and that's a graph of how it changes. And notice that we're going to be focusing on slope, right? A differential, a delta or a differential is a slope. It's how something is changing. The when and how fast the magnetic field is changing in a circuit will become a very important detail in regard to transformations of energy. And more specifically, because we're going to be looking at wire loops, there's going to be a dependence on the current I. So how the current is changing in the circuit will be a very important factor for us to keep track of. We're going to take a look at the details of how to develop the idea of mutual inductance and inductance in general. And so we're going to start with 2 elements here. We have a solenoid and a coil of loops. And the definition here, the foundational concept here is a changing magnetic flux through one induces a current through another. And again, we're invoking Lenz's law and Faraday's law here. Those are the 2 foundational laws. So what we're going to see happening is that there's no initial current through the large coil. So I'm going to label that 2 here. There's no initial current through that large coil. And there's an increasing current I1 into the solenoid. So I1 is going into the solenoid and coming back out. There's I1. So we're going to let there be a dI1 dt. And so when I look at the induced EMF in E2, or in the coil, that's the induced EMF in the coil here, I'm going to be looking at how the flux through it changes, okay? So that depends on the number of loops of that coil, the area of that coil, so that's the larger object in there, and a changing magnetic field through that coil. But what I'm going to note is the magnetic field through that coil is due to the solenoid and the current in the solenoid. So that's why I put a dB1 in there. We're going to note that the angle between these two area vectors and the magnetic field is going to be 0. So we're going to get a cos 0, which this term will turn to 1 overall. And I'm going to note again that there's two separate currents. There's an initial current from this power supply, which is causing the magnetic field. So I'll write that out, causing the magnetic field. And then there's the second one, which is the result of this changing flux through the loop, and that's from electromagnetic induction. I'm going to remind you, once you find an EMF, you can relate it to I and R in order to find a current, and this would be I resultant. Okay, so two separate currents. So let's work with a little bit more detail and head towards our relationship of how to get to mutual inductance. So simplifying this previous equation, right? I had E2, the induced EMF, is D, the change in flux in the second loop. So we're going to look at this larger area here. So that's A2. Okay, I brought the differential out front, and what happens here is physicists are kind of clever. There's multiple ways that you can look at this equation, and where mutual inductance, where this value M comes from, is that it lumps a bunch of things into, when I take this differential, I have a number of loops, I have an area, I have a mu naught, and some sort of expression of N1 with some geometry of the current carrying loop times I1. And the only thing that's changing in here is I1. Remember, the I1 going into the loop, that's the only thing, into the solenoid, that's the only thing that's changing. The rest are constants. And so when I take a differential, you can just bring the constant out front, and the differential stays with the current. And all of these constants, N1s, N2s, areas, links, what have you, get lumped into this term M. Okay, and M is what we call the mutual inductance, and it depends on the geometry and the number of loops of the two circuit elements involved. So here we have a solenoid and a loop. You could have a solenoid and a solenoid. You could have a loop and a loop. Okay, but we're looking at that geometry, and that's what mutual inductance is. And again, because the flux depends on the geometry of the loops, then the mutual inductance depends on the geometry of the loops. The direction will always be given by Lenz's law. I'm going to note here that the flux through loop 2 is also the flux through loop 1. If I look through at the flux through this loop, the larger loop, it's going to be the same flux through this smaller loop. Okay, and the flux through the smaller loop is going to be A1, B1, right? The flux through here is going to be the area of the solenoid and the magnetic field caused by this solenoid. Okay, so without doing a bunch of algebra here, I'm not going to worry too much about that. I'm just kind of wave my hand and saying we're going to put all these constants into this term of mutual inductance, and you can calculate mutual inductance with this expression. And we're going to keep the di dt out back here. And these are going to be the two relationships that are going to be most useful to you as we move forward. Okay, so I have chosen a problem to keep talking about this concept and an application of it. So my first example here is inductance as a constant of proportionality. And you may have noticed that this is a constant. I just have a constant of proportionality out front here. The EMF is the slope of this I value multiplied by this constant of proportionality. So When the current in one coil changes at a rate of 4.7 amps per second, an EMF of 6.8 millivolts is induced in a second coil nearby. What is the mutual inductance of the two coils? So they want us to find M. What is M? Okay, and you saw in the previous slide, there's a couple of ways. There's these two equations, formulas that would let me find M. If I know the EMF and the changing current, or if I know the N and the flux and the current through the different the loops. So what I'm going to note here, okay, is that again, we're going to be looking at changing flux through the second coil. And over here I have two different coils. I have coil 1, so this one is coil 1, and the other one is coil 2. And they're telling me, all right, that the changing current through coil 1, this is coil 1, is given by this value. And I drew the graph of this, right? And so I can say the change in the current over change in time is the slope of this line. And what happens is that the changing magnetic field, B1 here, this magnetic field is going to change in time, and it's going to cause this EMF. So this is EMF, and this is I1. As the current through 1 changes, it causes an EMF in loop 2. Okay, and our relationship is that the EMF in loop 2 is M times the slope of that first graph. Let me write out slope correctly. Okay, that's the relationship. If I want to find this EMF, I would take M and multiply this slope. And notice that this is a constant value through time, right? It doesn't say exactly here. It says when the current in one coil changes at a rate of 4.7 amps per second. It could be some curve here. I just assumed it was constantly increasing. So if it's constantly increasing, the EMF is going to be a constant value. So this EMF is created in the second loop. Okay, the first loop has a changing current, and that induces an EMF and a second current in that second loop. Because this magnetic field is changing through the area of that loop, there's an induced electromagnetic force, electromotive force. So that's why there's an N2 and an A2 and a B1. The magnetic field going through the loop 2 is B1. Okay. So let's finish this problem out now that we kind of have an idea of what's going on. And so if I want to find the mutual inductance, I'm just going to take E2 and divide by the value of how the current changes. That's it for this problem. Okay, I don't have any other information I'm given. So it could be, you play with your calculator long enough and you get this answer. But now you know why. We're just going to take these two values and divide them. And when I do this when I run this through my calculator, I get 1.4468, and I'm going to leave the 10 to the negative third on here and call it millihenries. Okay. So I think it's important here to get a good picture going. I didn't draw one, but you can draw two different loops, right? Loop 1 and loop 2. We're going to note that there's a current going through loop 1, and there's a reactive current induced in loop 2, an EMF induced in loop 2. I have a second example. This is one I pulled from University Physics. It's the example in there, and I wanted to give a little bit more commentary and provide a graph here for this problem. I snagged the picture for it. This is the original picture when I started talking at the beginning of this lecture for this problem. a long solenoid, so they give us the length of the solenoid. And I think it's important for you to write out the information with good symbols. I'm going to call this L1. They have it labeled in the picture. I'm going to call it L1. This is L1, is 2.7 meters. They tell me radius 1 here, radius 1, little r1 is 5.9 centimeters, and n1 is 250 turns. Okay, so that's the information for the solenoid, which is, it says if the current in the solenoid is changing at a rate of 790 amps per second. So that's what I have here. You can notice that the current is going in here like we talked about before. So this is I1 as a function of time. And in response, the EMF in 2 as a function of time is going to be some value. And it is going to be related, again, m times the slope of that line. Okay, so the change in current over the change in time, that equals the slope of this line, and they're telling us it's 790 amps per second. Okay, and that's how I1 is changing. When I look at this loop, I1 is changing at this rate. Because the magnetic field in this area is changing, then it will induce a current in the second loop, I2, which is related to E2. So that's this here, down here. And they want to know, what is this value? It's not given in the problem. In the prior problem, it was given as a value. But here they want to know what it is. So it seems like I need to work with this situation. They give me the slope, that's 790, but I need to figure out what the mutual inductance is between these two, the solenoid and the coil loops. Okay, so I'm going to be using the second relationship here, M. And let me write down, let's see, R2 is the coil. It has 3.5 meter radius, and N2 is 49 turns. So we'll keep those N1s and N2s and Rs separated so that we can keep good track of them. So let's look at the mutual inductance. Mutual inductance is N2, flux 2, which I will say is A2 B1 cosine of 0 degrees divided by I1. Okay, so this up here is actually the total flux through the loops, the coil. There's one loop, and then you multiply it by n 2 times, right? Okay, so let's plug these values in. N2 is 49 turns, okay? A2 is going to be, and I want to be clear here, is whatever area the magnetic field is in, right? When I'm looking at flux, the magnetic field does not go through this whole area. It actually goes just through this tiny area of the solenoid. So I'm actually going to put an A1 here. So when I look at A1, I'm going to have pi R1 squared. And then B1 is caused by the solenoid. So the magnetic field of a solenoid is mu naught N1 over L1 times I1. Okay. Cosine 0 is 1, and then I divide by an I1. So a little preemptive with this 49. I still have everything else in symbols. Notice that the I1 cancels on top and bottom, which is fine because I don't know I1. They just tell me how it changes. They don't tell me what the value actually is. So when I look at this, I have an N2, and I have an N1, I have the radius, and it's the radius that contains the magnetic field. So I'm going to plug the numbers in here. I'm going to have a 4 pi, or 49. I have a pi times 0.059 squared, the radius of the solenoid squared. Mu naught is 4 pi times 10 to the negative 7th. N1 is 250. L1 is 2.7. And that's it, right? The I1s cancel. I have everything else plugged in. I have both ends in there. I have an area. I have mu naught. I have the length of the solenoid. So when you calculate the mutual inductance, you get, at least I get, 62.35 microhenries. So the units of inductance is a henry, after the physicists that worked with that. So that's the mutual inductance between those two. Remember I said that the mutual inductance depends on the flux through the loop and thus the geometry of the loops. And we have the geometry of the loops in here. Once you get the mutual inductance, we can go up to the first equation and say, oh, E2 is going to equal that value, 62.35 times 10 to the negative 6th. And we're going to multiply by di1 dt. di1 dt, they tell us, is 790 amps per second. So when you run this through your calculator, you will get 0.04926 volts, or you could call it 49.26 millivolts. Okay, so that's good. I think mutual inductance is an interesting concept. If you have a changing flux in one coil, it's going to induce an EMF due to changing flux in a second nearby coil. So the interesting case is moving towards how do we use this in a circuit? And that's the concept of self-inductance. And you might have suspected this before, like, okay, if I change the magnetic flux in one coil, it induces an EMF in another coil. But if I change the EMF in one coil, will it induce an EMF in itself because there's a changing magnetic flux going through the coils? And the answer is yes. This is what we call self-inductance. So in the text here, I said a changing magnetic flux due to the changing current causes a back current and an induced EMF that opposes that change in the same set of loops, whether it's a solenoid or a loop, coil. So an inductor is actually a solenoid. It's just a bunch of loops stacked up on itself. And instead of having E equals negative M di dt, we have an L in here. So that's just the difference. M is for mutual inductance and L is for self-inductance. Inductance also is measured, self-inductance is measured in henries as well. Okay. So the relationship's true whether there's an M or an L here. The EMF is this constant of proportionality multiplied by the change in the current, whether this is a differential or just a linear, delta. And also, without going through the derivation, the self-inductance of a solenoid or coil is the total flux going through that coil divided by the current. And this is the initial current as it changes, right? This will be the changing initial current. That outside current, whatever is being put inside of it, has some change to it. It's changing over time. Okay. A and B, the area of the loops and the magnetic field of whatever the inductor is depends on the geometry of that inductor. So you'll have a radius in here, you'll have a length in here, you'll have an n number of loops in here, and all of that stuff is important in order to figure out the inductance of the self-inductance of that circuit element. I will say that because this is a known fact, if I send current through in one way, I'm going to get some what we call a back current. It's a back current, back EMF in one direction. You can actually wisely design an inductor, a coil, that has no back current by just taking it and winding it one direction and then looping it back again, right? Do you see that? There's current in one direction, there's current in another direction. This was taken from OpenStax University Physics Volume 2, where it's the heating coil in a dryer. And of course, we don't want a current going through. We don't want any electromagnetic induction in the metal case of a dryer. So in order to counteract this effect of self-inductance in the coil, they just wrap it back on itself. So there's as much change in flux or current in one direction as there is a change in flux or current in the other direction, resulting in no back current, no EMF here. Which is good. That's a good thing for your dryer. But in circuits, we may want to have some sort of effect, because what happens is there's an induced EMF, there's an induced magnetic field, there's the original magnetic field due to the current, there's an initial magnetic field, and then there's a back magnetic field in response to that initial changing magnetic field. That initial magnetic field changes with time, and Lenz's law and Faraday's law says that there's going to be a one proportional that opposes it. We like this in circuits because it allows us to store energy in the electromagnetic field. Okay. One thing I wanted to address here, which comes up in some problems, is, and we'll look at it when we get to LC and RLC circuits, is that this back EMF, this back current, causes what we call a reactance or a resistive reactance, a resistive property. And so there's a voltage drop over it. If there's a back current and there's a back EMF, there's a voltage drop over this circuit because of the back current. Sorry, it's not a circuit, it's an element, right? When I look at a resistor in a circuit and the current's going one way, I can say that there's a positive and negative end of the resistor because there's a voltage drop in one direction, and this would be for a resistor. The same thing happens for an inductor. So depending on the direction of the current and which direction, let's say this current is moving in this direction and that it's increasing. All right, if there's an increasing current, well, that means that overall the back current will cause this to be a high end and this to be a low end. I would get overall a drop over this inductor because it's causing a back current and some resistance to the flow of the original current. Okay, so if you see any problems like that, you can think about that way. I've picked out a couple of examples for us to work through. The first one is magnetic flux per turn. It was an example. It's an example in the University Physics Volume 2 book. I added a couple of graphs here and can explain a little bit more in detail about what's going on in this problem. And one thing is that it's there's no picture. I think one thing that you want to do for these problems is draw a picture. It says an induced EMF of 6.1 volts is measured across a coil of 27 loosely wound turns. So when I look at this, I'm going to have a coil. A coil is different than a solenoid. So this is just a big loop, a bunch of big loops. It doesn't have the structure of a solenoid. A solenoid looks like this. All right, that's a solenoid. Here we're going to assume that the length of this thing is really, really short, such that it's not even a factor. So it's not a solenoid, it's a bunch of loops. Okay, and so when I think about the magnetic field of a loop, I'm going to have mu naught I over 2r, and then factor it by n if there's n number of loops, right? So here we have 27. We're not going to use this equation here. Notice that there's no radius given, but just drawing this picture here and remembering what you're working with is an important thing. So going through this loop, I see that they give the current as it increases uniformly from 0 to 3.9 in 0.69 seconds. So I drew that up here. Here's about 0.7, and there's some sort of change in current over change in time. This is the current, this is the time axis. And in response, it has an electromotive force, an EMF, a resulting EMF that is constant through time, right? Because this EMF is going to be the slope of this line multiplied by L. L times the slope of that line. So what they want is, what is the magnetic flux per turn at this maximum current? So we're noticing at the end there's I max. I max is 3.9 at the end of the 0.69 seconds. Okay, so they want to find what is the flux per number of turns. Okay, so we want flux in here. And they give us a changing current over time, and they give me an EMF. So I can see that L is going to equal the EMF divided by that value, di dt. Okay. L also equals the number of turns times the flux per turn over I. So we're going to isolate what flux is here. So if I do some algebra, I get flux equals, okay, the EMF times I max, because we want the the magnetic flux per turn at this maximum current, so I'm at I max, and then we're going to divide by N times di over dt. Okay, so di dt, change in flux over change in time, that should be easy. I go 3.9 amps over 0.69 seconds. So you could calculate it as a value. I'm not going to do that. So overall, we're going to get 6.1 times the max current is 3.9. The number of turns is 27. And di dt, 3.9 divided by 0.69. I'm going to note that the 3.9 is on the top and bottom, which is typically true. The current will cancel here. It doesn't matter the value. It depends on the geometry more. So I get 6.1 times 0.69 divided by 27. And when you run that through your calculator, you get 1.53 repeating. And I'm going to remind you that flux has units of Webers, and that will be the answer. And that's Webers per turn. If I wanted the total flux, I would take N times the flux for one turn, right? This is just one turn. That would be the total flux. So this is Webers per turn. Okay. And notice again that the EMF is directly related to the slope of the current, how the current changes, multiplied by this constant of proportionality self-inductance. One thing that you will be required to do is calculate the self-inductance of any, set of coils or solenoid. Can you calculate the self-inductance? And I'm going to remind you, you can calculate self-inductance here by calculating N flux over I, and on the previous problem, I'm going to note that we had the I canceling on the previous problem, and it'll happen here too. It says a solenoid with length 0.14 meters, so 14 centimeters. So here's a solenoid. It has a length L. I just call it script L. I do this because L, big L, is inductance, so I just make a script L so that I know the difference between L and L. It has a radius, so L equals 0.14 meters. There's a radius here of 0.012 meters, and the N value is 685 turns. Okay, so those are the important geometries and configurations of our element here. So let's plug what we know into our L equation. We want to calculate L. We're going to take N. Let's look at flux for a second. Flux will be AB cosine of the angle. We're going to assume that this is the coils are at a 0 degree orientation with each other, so this term becomes 1. The magnetic field will be the magnetic field of a solenoid, which I'm going to remind you is mu naught N over L times I. And then the area is for a circle, area is pi r squared. I'm going to have a mu naught N over I. N over L multiplied by I times 1 divided by I. And notice again what I mentioned before. This shouldn't depend on the current, which is good. I'm not given the current. I can't actually calculate the flux, but we're normalized. The flux is normalized per unit current. So notice I have an N squared here. So I'm going to take 685 and square it. There's an N here and an N here. I'm going to divide that or square it. I have pi times the radius squared, 0.012 squared. I have a mu naught, which is 4 pi times 10 to the negative 7th. And then I'm going to divide that all by the L here. Okay, so divide by L, which is 0.14. Does not depend on the current. I can calculate the self-inductance of a solenoid, of an inductor, without there being any current through it. I don't need to know the current. So when you run this through your calculator, you will get 1.91 times 10 to the negative third. So I'm going to write millihenries here. So that's how you do that. If you had, for instance, a set of coils rather than a solenoid, you would need to use B equals mu naught I over 2R. Again, it depends on the geometry here, whether you have a solenoid or whether you have a set of coil or also what we call loops. Those are the same name here, or same geometry, different name. But we definitely have a solenoid, so that's why I put that in there rather than mu naught I over 2R, different geometry. So hopefully that gives you an idea of what inductance is, right? It's the resulting EMF based on a changing current. And it happens in a situation with mutual inductance. We have two different elements where the changing current in one induces a current in the other. And you can have self-inductance where a coil creates its own back current, and that's what we use in circuits. And we need to know that this is a back current and how to use it in circuits. So as we move forward to RL circuits and LC circuits and RLC circuits, you're going to see how this back current, this DI/dt, the EMF with the changing current, plays into how a current acts, how a circuit acts, and the frequency at which we can drive circuits.